What do you do when you're a high-caliber mathematician or a scientist and you want to share your algorithms and code? Sounds like a job for GitHub, doesn't it? But the problem is, often this work is done on proprietary platforms such as Magma, Matlab, Mathematica, and others. Not only can you not share your licenses for, say, Matlab, but there are often proprietary, separate libraries and tools for specialized work. These are expensive products. One example from my distant past was using the Wavelet toolbox on Matlab. Matlab itself is over $2,000, and the Wavelet library is another $1,000. So to share my code, you must have both licenses yourself. This is a problem. Well, if you're William Stein, you take this problem and you turn it into an opportunity to build an open source competitor to Matlab and related platforms. This episode is all about SageMath, an open source, feature-rich option for scientists and mathematicians, built by over 500 contributors and consisting of over 500,000 lines of Python and Cython code. This is Talk Python to Me, episode 59, recorded May 10th, 2016.
I'm a developer in many senses of the word, cause I make these applications, but I also use these verbs to make this music. I construct it line by line, just like when I'm coding another software design. In both cases, it's about design patterns. Anyone can get the job done, it's the execution that matters. I have many interests, sometimes.
Welcome to Talk Python to Me, a weekly podcast on Python, the language, the libraries, the ecosystem, and the personalities. This is your host, Michael Kennedy. Follow me on Twitter where I'm at mkennedy. Keep up with the show and listen to past episodes at talkpython.fm and follow the show on Twitter via @talkpython. This episode is brought to you by Hired and SnapCI. Thank them for supporting the show on Twitter via @hired_HQ and @snap_CI. During the conversation, we talked about running SageMath on Windows and some of the challenges there. We mentioned that the new Ubuntu subsystem coming to Windows 10 this summer may make this easier. Well, just after we recorded this episode, someone did indeed post a message to the SageMath mailing list showing it running on the Ubuntu subsystem on Windows 10. So look for more goodness in that area down the line. Now, let's chat with William. William, welcome to the show.
Thank you.
Yeah, it's super exciting what we have to talk about today. We're going to talk about building quite a large ecosystem of computational mathematical tools with Python and a bunch of other related technologies, Cython, C, IPython, lots of stuff, right?
Mm-hmm.
Yeah, it'll be a lot of fun. But before we get into it, of course, tell me your story. How did you get into programming and Python? You're a mathematician by training, right?
Yes, yeah. So I've always been into programming since I was like 5 years old, but I got very much into mathematics. As an undergraduate, I was a computer science major for a little while, and then I switched to mathematics since I love it, especially number theory. And then I went to graduate school at UC Berkeley from 1995 to 2000. And while I was at graduate school, I got heavily involved into computing with various objects that come up in number theory. And so I had to write a lot of code in order to compute with those objects. So I just wrote a huge amount of C++ code using a lot of the libraries in the mid-1990s. It was really painful. It would take like 30 minutes or an hour to compile, did lots of templating. And I wrote a little interpreter so I could create modular forms and other mathematical objects and compute with them. And I was doing this sort of all in isolation without using much beyond some C++ libraries. And then I found out about a computer algebra system called Magma, which was extremely powerful for computing in abstract mathematical domains. It's in a way kind of a competitor to Mathematica or Matlab, but aimed much more abstract mathematics. So it has heavy support for group theory, abstract algebra, graph theory, etc., and very little support for symbolic calculus. But it's what I needed for my PhD thesis work, so I worked really heavily on it. It's an extremely powerful system, and I wrote maybe 30 or 40,000 lines of code that are included with that software. I went down and visited them in Sydney, Australia a few times. But one frustrating thing about Magma is that it's closed source. I saw a talk by Manjul Bhargava, who recently won the Fields Medal, but back in 2003, he was talking in Paris about using Magma for some research on quadratic forms. And he was running into some brick walls due to it being closed source. And I also kind of took stock of my own computing environment at the time. I used Linux, LaTeX, Emacs, and everything on my computer was open source except Magma, which was the one program that I cared about and which really mattered for my research. So I thought that was ridiculous.
Right. That's the most important thing. Yeah, the most important thing that you actually were working with was the one that you had the least control or visibility into, right?
Yeah, exactly. And at that time, I was also using Python a lot, not for mathematics, but for kind of scripting mathematics. So if I wanted to do a bunch of computations on a cluster, I would write little scripts via Python to start up the computations. I wrote websites using Python. So I was using Python a lot kind of as a complementary tool to mathematical computation. And so I was at least familiar with Python because of this. And it was back in 2002, 2003 when Python was more primitive than it is now.
Right. That's just a little before it started to get its scientific legs under it with things like NumPy and SciPy. And it wasn't quite there, but it was on the verge of that breakout, right?
Yeah, but it still was a pleasant interpreter environment, and it had modern features like multiple inheritance. You could define your own data types, had good exception handling, etc. And so I really appreciated some of the functionality it had over, say, Magma. Magma, though it has a massive library and is incredibly powerful, it misses a lot of basic features of a modern programming language, which by modern I mean, say, at least as good as C++ in 1993. I was used to at least having exception handling and being able to define my own classes and so on.
Right. That's one of the challenges of not just Magma, I would say, but things like R to some degree, Matlab, Mathematica, all these various highly specialized tools that are great at solving some type of computation or some kind of problem. But when you have to go and build a full application out of it or something, it kind of hits a wall, right?
Yeah, exactly. There are a whole bunch of special purpose math languages designed by mathematicians. And though they are pretty good for mathematics, they don't really compete with what you get when you have computer science people systematically put full-time effort into designing a language and then a whole ecosystem around that language. And so the difference between trying to write a non-trivial program in Python versus Magma is that with Python, you have this massive ecosystem of tools plus a language that's very general purpose. Whereas with Magma or Mathematica or Matlab, it's really good maybe for parts of the math things, but for the other parts, just manipulating strings or whatever, it can be pretty painful.
Yeah, absolutely. So you were working with Magma and you couldn't really use it in the way that you wanted to, sort of like a web front end or as the back end for a web front end. And that's one of the problems you run into a lot with these types of software. I'm specifically thinking of Matlab because I have the most experience with it, but there's all sorts of little, pay for this bit, pay for that bit. It's registered on that machine. Like the rules are just crazy, right? And so you got frustrated with this, yeah? Yeah.
So in particular with Magma, the project director sent me a message saying that I wasn't allowed to use it as a general purpose compute engine on the back end for my websites. And that was very frustrating. It wasn't just a matter of pay them or not pay them or get the right license, since they're a little more informal than that. They don't really have kind of official licenses. So that was like a huge wake-up call that I really needed to do something. And so I decided I was going to survey the open source landscape again for math software and see what's out there and then switch. But when I looked around, it was really kind of frustrating back then. There were a number of programs that kind of competed with Magma, but were much more specialized. And despite Magma's language being fairly primitive compared to, say, Python, the other systems had languages that were much, much more primitive yet. So, I mean, it's kind of hard to emphasize how primitive they are. It's kind of like using, assembly programming. I mean, things like different namespaces, that sort of thing is an advanced feature compared to what's available in some of those languages. So I couldn't really bring myself to go back to that. And also there's a huge amount of functionality that got implemented in Magma over about a decade, and it just wasn't implemented anywhere in open source, which was a serious problem as well. So there was just a massive lack of functionality. So what I decided naively first to do was just choose a language, and I spent about 6 months to a year evaluating options like OCaml and directly writing something myself in C++ and using Python. And at the end of the day, I chose Python because the language was most similar to Magma's. And so I thought it would be easier to get users over from Magma. And also the Python C API was kind of like what Magma had, but much cleaner as far as how Magma itself is implemented. And so one thing about Python is that if you want to write a function that you can use from the interpreter and is really fast, you can write it in C if you need to, and it's just as fast as if you wrote it in C. And that's kind of a basic requirement if you're going to write code that will be used for research, that you can write very, very fast code. So Python was good enough, and then I decided I would just sit down and Python, C, and me, and I would look at maybe code from other projects and look up algorithms and implement everything I needed. And this lasted about 3 hours. And I realized how insanely hard that would be to do. And I completely switched courses and decided that purely out of laziness, I would try to wrap existing code in whatever way I had to do so. So using pexpect, sudo-tty type stuff, using C libraries or adding C libraries to existing computer algebra systems, etc.
So maybe not everyone knows expect. Actually, a lot of people don't know. But they know C, of course. But what is pexpect? So
one way, if you have a, say, Python program and you'd like it to interact with some other kind of bizarre, let's say there's a program called Mathematica or something. Just one researcher wrote it, has a command line interface, and it doesn't have any C library interface or anything. But you really want to call functions in there and run some code there and get the results. What pexpect will do is let you basically simulate the terminal and use Python to programmatically feed code into the other program, look at what output it produces, and then parse that output and return it. So it abstracts things away and makes it look like you're calling some functions in a Python library, but really behind the scenes, things are really more or less being copy-pasted into a terminal. It's nice because you can interface with a closed source black box this way if you need to. And the drawback is that it's brittle and it's potentially slow. There's a lot of latency. There's a several millisecond overhead to every single thing you do, which is painful. You really want the overhead to be a microsecond, not a milliseconds. So there's like a order of magnitude of 1,000 latency, which can be really annoying.
Interesting. So yeah. So you were naive and hopeful, and you just said, I'm going to go write this. And then you basically decided, all right, forget that. Let's try to find all the good building blocks that are already built and build upon them. And that's a very open source way of problem solving anyway, right?
Yep. So I think about it this way. Like when I worked with Magma, my team was all the other people, working on that project. And when I switched to trying to do something open source, the team was all other people in the entire open source sort of world. Everybody that contributed to open source. And definitely the easy way to go would be to choose the best libraries for number theory and commutative algebra and graph theory and so on and put them all together. And they weren't kind of built to be put together or to be called from Python, but no matter how hard it would be, it's way easier to provide a library interface to one of those other systems that you can then use from Python very efficiently than to write one of those systems from scratch. Like each of those systems took decades and decades of work to write. So, total.
Yeah, and to debug them and fine tune them and, that kind of stuff's very hard to know, even if it's right some of the time.
And a lot of the algorithms, you really kind of have to be in the throes of a PhD focused for years just to understand what the algorithms are and how they work. And there's just no way one person can replicate that despite wanting to.
It was a good idea. That's interesting. Yeah. So in the end, you decided, all right, Magma is cool, but it's got all these restrictions, and I'm going to go put this thing together. And what you built was called SageMath, right?
Yes. Yep. So I built SageMath, which is, basically what it is it's a Python library, but many of the dependencies are these tricky to compile C programs or Fortran programs or whatever, which were written by mathematicians only to run on Linux, maybe just for their research. And so in addition to just being a Python library, it's also a build system, kind of like Anaconda, but obviously a little bit before that. And it targets a different type of dependency, different types of packages. It's a build system. It's a Python library. And then to make it more friendly for mathematicians, it has a customized IPython command line. And also around 2006, we wrote web-based graphical interface, which is like the IPython notebook, but we wrote it a few years earlier. And it was before things like WebSockets and a lot of nice modern JavaScript functionality existed. So
back in the dark days of JavaScript when it was earning its bad reputation.
Yep, we started writing it right when I think Google Maps and Gmail appeared, and there was this thing called Ajax, which let you update a web page without refreshing. And so we had that little bit of functionality. But the thing we didn't get was a persistent connection. So instead we had to do polling techniques and all kinds of tricks that were ugly.
Yeah, very interesting.
In order to make it like, when you do a for loop in Python, you want to see the output as it appears. And in order to do that, we had to do a lot of hacky stuff.
Yeah, so I think the way maybe to conceptualize it is this is an open source alternative to something like Mathematica.
Exactly.
Or Matlab maybe, but it leverages a lot of the good data science, scientific tooling of Python, like IPython notebooks, for example.
Exactly. So initially, I just wanted it to be good enough for my number theory research, number theory being my research area. But the second developer wasn't a number theorist. The second person I could get on board did research in coding theory. And so he wanted a bunch of functionality that had little to do with number theories. And then he also wanted to teach undergraduate courses like calculus and differential equations. And so I started adding a lot of functionality related to those classes just so that the range of applicability would get bigger and I could get a few more developers. And things started growing that way. And so the system quickly went from being just for number theory to being much more general. And in order to kind of focus development and decide what it should be, we chose the motto or the mission statement to create a viable open source free alternative to Magma, Mathematica, Matlab, and Maple. Our focus, none of the developers really have a focus on numerical computation. So in Sage itself, in the Sage library, focus more on algebraic aspects of things. So arbitrary precision arithmetic, working very quickly with large integers and rational numbers, doing linear algebra where you have no round off error, that sort of thing. And for the more numerical parts, the kind of viable alternative to MATLAB, we just incorporate libraries like NumPy, SciPy, etc., which the Python community has done an amazing job of developing over the years.
Right, and that's definitely gaining speed now, right?
Yeah, it's absolutely incredible now. I mean, we wanted all along to be a viable alternative to MATLAB, and I remember in 2006 trying to write statistics functionality and all this kind of stuff for Sage directly, and just being like, I don't want to do this at all, but it's part of what we're trying to do to get more users, so here I am doing it. And I'm so happy that the community has come along and just made Python absolutely first rate in statistics and numerical computing so that we can just incorporate that functionality.
Yeah, that's really great. One thing I think before we get too far into the details would be interesting for the listeners is just the scale of this project, the number of developers, number of lines of code, the technologies involved. Could you just give them like a quick sense of that?
Sure. So the project itself incorporates about 100 packages. We have done a lot of development at what we call Sage Days workshops. And those, we often have about 10 to 15 per year. We've had, I think, 80 Sage Days workshops so far. They're kind of inspired by the PyPy workshops that happened about a couple of years ago. But basically, we come together for a week and do lots of development. The number of contributors to Sage is around 500. So those are people who have contributed directly to the Sage library. Of course, Sage itself incorporates all these other open source packages, which have their own contributor groups. The amount of source code, I don't know the exact number, but it's on the order of several 100,000 lines of actual code. And the code is about maybe 60% Python and maybe 40% Cython code. So there's a very, very large amount of Cython code that we've written. And functionality-wise, we do cover a very wide range of areas of mathematics. So almost anytime somebody comes to use it, they find that like there is something for the area of math that they're interested in.
This episode is brought to you by Hired. Hired is a two-sided curated marketplace that connects the world's knowledge workers to the best opportunities. Each offer you receive has salary and equity presented right up front, and you can view the offers to accept or reject them before you even talk to the company. Typically, candidates receive 5 or more offers within the first week, and there are no obligations, ever. Sounds awesome, doesn't it? Well, did I mention the signing bonus? Everyone who accepts a job from Hired gets a $1,000 signing bonus. And as Talk Python listeners, it gets way sweeter. Use the link hired.com/talkpython to me, and Hired will double the signing bonus to $2,000. Opportunities knocking. Visit hired.com/talkpython to me and answer the call. That's awesome. That's a really large-scale project, and I think it's a cool success story. So it's written in Python and Cython, which is kind of a flavor of Python, but you also chose Python as basically the programming language of the system itself, right? Like Matlab has its .env files with its own language, Mathematica has their own language, but you sort of said, hey, Python is a good match for the mathematicians.
Yes. So this is a decision that I made, I would say, purely out of laziness originally. As a CS undergrad, I had written an interpreter, I took a course in writing interpreters, and I had tried to do that again for some of my number theory research. And I also had just seen how hard it is to really develop a programming language, and I really didn't want to do it. And moreover, the Magma group, I had often made requests for them to improve their language, and they responded that though they could get grant funding for the mathematical algorithms, they had a huge amount of trouble getting any funding for the actual language because their funding sources were in mathematics. So I was kind of scared for a number of reasons off from writing my own language. And basically, I'm like, well, it just follows the same principle of reusing third-party libraries and computer algebra systems to reuse a third-party language as well. I decided to use Python. It was criticized a lot by math people because literally every other project like Sage that's ever happened up until that point made up their own language. It was kind of like the thing you had to do.
How has that criticism changed over time? Do they still feel that way, or has it become more accepted?
Way more accepted. And it's now considered a huge advantage. And often when I hear people convincing other people to switch from Mathematica to Sage at all levels, both at research and undergrad teaching, one of the biggest, maybe the strongest arguments is that Python, the language, is just a better language because the syntax is easier for the students and it prepares them for other possible employment opportunities and down the line. So
that's pretty interesting because when I was studying math at university, I did study C++ and Scheme and other things because I took some computer science classes, but my math education really taught me just the Matlab language, whatever you call that. I'm sure there's a name for it, but that's a very limited skill set to take away if I go out into the job market, right? But if people, as part of learning their math and doing their research, their statistics, whatever, become semi-proficient in Python, just sort of silently in the background, that's a really cool side effect.
Yeah, and I have had many PhD students who learned Python really, really well as a result of working with me, and they really do use it in their jobs today. Like one of them, Robert Miller, who wrote a huge amount of our graph theory functionality, now works as a data scientist at Google. And another one, Simon Spicer, also works as a data scientist, but at Facebook. And they use both of them use Python really heavily in their jobs.
That's cool. Do you know if they use SageMath there?
I don't think either of them use SageMath for their jobs, but I do know that SageMath is used at Google by some people, but not necessarily my students.
Okay, yeah, that's very cool. What would you say to people who are maybe just straight up using NumPy or Matplotlib today? Maybe they're using an IPython notebook. Like, should they consider using SageMath, and what would it offer them?
It depends on what you're doing, but so SageMath does symbolic things, and it can be very efficient at doing them. Like you have a large matrix and you want to do something with it, and you want to have no rounding errors at all, or you want to do something with linear algebra over finite fields or coding theory. Basically, Sage provides a lot of functionality that's complementary to the numerical things that are offered by NumPy and SciPy. It overlaps some with SymPy, SYMPY, though it has a lot of functionality that isn't in SymPy, and in many cases it can be a lot faster. So, also another remark is that Sage now uses Jupyter notebooks as our default graphical user interface. So when you download and install Sage, you get Jupyter notebooks. One big drawback, which I hope to address in the future, is that currently, by far, the easiest way to use Sage is to install our self-contained distribution. And it's completely separate, really, from PyPy, the Python packaging repository. And it's not something that you can just install into your own Python environment.
Right. There's no pip install SageMath. Yeah.
Not yet. Yeah. I really, really hope there will be in the future, but right now that isn't the case.
Right.
And so that interferes with easy adoption by existing Python users.
That's true, but you do have a pretty decent way of getting it. You can go, like, on the Mac, you can go download just DMG, just a disk image, or on Linux, you can get a tarball. And it's kind of all self-contained there, so it's not too hard to get started with, right?
Yeah, a lot of our users just want to do math rather than deal with an installation. And so we do put a huge amount of effort into making it easy to just install. So we have Windows, Linux, and OS X binaries ready to go. The Windows one currently is a virtual machine that you run. And then it provides a server, and then you get a Jupyter notebook that you can use Sage through.
I see. So maybe you run Internet Explorer, but then you're requesting back into like a Linux thing on a virtual box or something?
Exactly. Yeah, that's our main supported environment in Windows right now.
Okay, yeah, that's an easier way to get some of those libraries to compile for Windows, right?
Yeah.
That is a seriously hard problem to get some of those libraries that were not built for Windows, the C libraries or Fortran, to compile there, right?
It's really, really hard. We tried for years and are still trying to natively port Sage to Windows. And I don't know if or when it will ever succeed.
Yeah, interesting.
It's like I don't know, in the Sage project, there's a lot of these sort of tall mountains that are very difficult to climb. And 4 or 5 people will try and fail, and then the 6th person will succeed. Like writing a really good implementation of working with what are called finite abelian groups was one thing where it just seemed like one person after the other tried and failed, and then eventually somebody got it. And I hope porting Sage to Windows will be a similar thing. Some combination of the right approach and Microsoft Windows getting more friendly to POSIX style programs.
Yeah, well, I don't know if you heard, you are in Seattle, right? So maybe you heard that Microsoft in this summer, they're shipping a new version of Windows 10, and it comes with the ability to run native Linux binaries on the command line.
Yeah, so that's just awesome. And Microsoft is going in the right direction, that we should have something that works natively by maybe using that. It sounds really likely, actually.
It's got to be a huge step in the right direction for you guys. So I don't know if it would fix it, but it's definitely not a negative.
Yep, absolutely.
So one thing that's interesting, well, there's a bunch of interesting things I want to ask you about this. Let's start with this one. So doing math is obviously computational, right? Computationally intensive, and having more computational power is key. On modern hardware, that means parallelism, right?
Yep, it can.
How does it leverage like multi-core machines? Does it support like computational parallelism and things like that in it?
So one thing that surprises me a lot over the years, at least in pure mathematics, the sort of parallelism that we have to do is usually what's called embarrassingly parallel sometimes. Mm-hmm. So somehow it's a lot easier than what people do in numerical computing with, earthquake simulation or whatever, where they have some big distributed computation and each step depends on previous steps. And there's lots of data flying all over the place and you have to use MPI or something to do it. So the parallelization that typically comes up is you want to evaluate some function f, 10,000 values of n. And so you just do it pretty easily and there's no real dependencies between them. So basically using stuff built around fork, you can do pretty good parallelization that works pretty well for us, as I've found. Yeah,
okay. So in the embarrassingly parallel case, you just basically split it across processes or something like that, and a problem is solved, right? They got their own GIL, but who cares because it's theirs.
And you also, if you use a database, so you can have a process startup, query a database for some things that haven't been done, do them, and put the results back in. So simple techniques like that have kept the community pretty happy. Somehow our parallelization issues aren't too ridiculously hard. There There are much more subtle, interesting, like low-level parallelization techniques that go into Sage, where there's some C library or C++ library some Sage developer writes. Like David Harvey is a guy who wrote some super fast code for polynomial multiplication, and it uses parallelization techniques. And so Sage just kind of, or really Sage via Python, just calls out to this library. The library happens to do things in parallel and then give back a result. And so there's lots of little places like that where we have libraries that just implicitly do things in parallel. They're like highly multi-threaded, and you don't even know they're doing it unless you explicitly look.
Right.
So there's that level, and then there's also the level of forking. I wrote a decorator for Python called Parallel, which is included in Sage. So you put @parallel before a function, and then if you call it with a list of inputs, it'll fork the process, call the function with each of those inputs up to the number of processors you have, and then get the results and give them back to you as a generator. So there's some little things like that are built into Sage, and it takes care of some possibly tricky surprises that would happen behind the scenes involving subprocesses and so on.
That's really awesome. That's a very Pythonic little statement you made there. I'm going to put a decorator on it. It's going to, fork this off and return it as a generator. I mean, that is really great.
Yeah, and it works really well. We have code that, like nested functions written in Cython that just happen to have an @parallel decorator on them, and then they'll fork and regroup properly. And the code itself is just probably 2 pages of code, maybe 3 pages. So it's not a lot of code.
Yeah, it's just getting the right concept or the zen of the style to make it really expressive or whatever, right?
Yep. There's a ton of pieces of little things like that all over in Sage where I would like to separate them out as Python libraries, like individual standalone Python libraries, and then have Sage pip install them as part of its kind of build process. So that would make them much more widely available to the community. And then when they're run in the context of Sage, they would know to do the extra things that Sage needs, and they wouldn't do those things otherwise. We also have a pre-parser. So for mathematicians, just an example, if you type 2/3 in Python 2, which is what Sage uses, you get 0, which is floor division. In Python 3, you get 0.666666, and neither of those are what pure mathematician expects. Pure mathematician expects to get 2/3, which is like an exact rational number. So in Sage, we have a little pre-parser. So when you use Sage directly via its own command line, which is this modified IPython interactive command line, it will take each line of input and then do a little bit of parsing to it. For example, when you type 2/3, it replaces it by integer of 2/integer of 3. And then that allows you to make your own custom integer type. And then there's a bunch of other things similar to that. Like, for example, when you use the caret symbol, which in Python means exclusive OR, a lot of mathematicians are used to that meaning exponentiation, because that's what it means in LaTeX.
Right. Not as opposed to double star or something like this. Yeah.
Yeah. It's really like, so in Sage, when you type the caret symbol, it gets converted to double star before it gets sent to Python. So mathematicians almost never do exclusive OR, but they do exponentiation constantly when typing in polynomials and all kinds of things. So it's this optional thing that makes the Sage interface more friendly to mathematicians. It gives us our own kind of new language, but in a very well-defined minimal way, which is just built on top of Python. And in most cases, the things that get pre-parsed would be invalid Python code. And it would be nice to connect this with Python packages. It would be nice if we could take this pre-parser and make it a standalone Python package, which Sage just happens to use. And maybe, like, we have various interesting functionality in there, like square brackets 1.10 gives you the list of numbers from 1 to 10. It's kind of like the notation you'd have in Matlab or Maple instead of using the range function. And there was a Python PEP to implement it, but it didn't get accepted. But so many Sage people wanted it, Robert Bradshaw just implemented it anyways and added it to the pre-parser. So it would be kind of neat if this whole pre-parser were made more generally available, and then Sage just happened to use it.
Continuous delivery isn't just a buzzword. It's a shift in productivity that will help your whole team become more efficient. With SnapCI's continuous delivery tool, you can test, debug, and deploy your code quickly and reliably. Get your product in the hands of your users faster and deploy from just about anywhere at any time. And did you know that ThoughtWorks literally wrote the book on continuous integration and continuous delivery? Connect Snap to your GitHub repo and they'll build and run your first pipeline automagically. Thanks SnapCI for sponsoring this episode by trying them for free at snap.ci/talkpython. Maybe it could even have different grammars for different areas, like maybe geologists do something different than mathematicians. Who knows?
Yeah, and so maybe somebody's proposing some great matrix operations to include in Python eventually, and maybe they get added to Python 3, but they're not in Python 2. You could use the pre-parser and still have those. And everything just gets converted to straight Python, so you could convert everything and then stick it in a Python library if you need to.
That's cool. You said that in your documentation, you say you have a UI kit for adding user interfaces to calculations and the app. That sounds pretty cool. What's the UI technology there, and how's that work? Do you remember?
Yeah, I'm not quite sure what that refers to.
Yeah, okay, no worries.
Yeah, sorry.
That was written long ago, right? Okay.
And there's a lot of people. The other problem is there's 500 contributors, so I have very limited knowledge.
Sure, no worries. I'll ask you another sort of math question. Like, so one of the things when you're writing scientific and especially mathematical papers for academics and so on is you use LaTeX. So you can very precisely express symbolic mathematics like integral signs and things like that. Mm-hmm. And this is built right into it, right?
Yeah, so the connection between Sage and LaTeX is, of course, mathematicians all use LaTeX. But for so we have a dunder method. Well, it's really just a single underscore method, underscore LaTeX underscore, and it's defined on most objects that you create in Sage. And it gives back the LaTeX representation of that object. It works a lot like the repr method in Python, but it's to give you a LaTeX representation rather than...
Right. That's awesome.
Yeah, so we have... And it kind of recursively goes down the stack. So if you make a matrix with entries that are rational functions over, some other thing, then there's automatically a way to turn that entire matrix into a LaTeX representation. And that gets used in the graphical user interface fairly automatically if you want, like in Jupyter Notebooks or in Sage worksheets. Also, we have a LaTeX package called SageTech, which lets you write a LaTeX document and then use commands like \sage right inside the LaTeX document. So you can write something like consider and then in $signs \sage, and then in braces you can put some expression and it will get evaluated using Sage whenever you LaTeX the document, and then the result's cached. And you can also put blocks of code and the output gets automatically put into your LaTeX document. So basically it makes it so your LaTeX document can have executable Python code, but it's really... there's a similar thing like this for just Python, but for Sage, it also gives functionality for graphics, and it knows that Sage objects can have a LaTeX representation, and it uses that automatically when typesetting the results.
Yeah, that's really cool.
So it's something that was written at the first Sage days way back in 2006.
Yeah, really nice.
Long ago. And it's been developed ever since.
So another part of this system that I think is really interesting is Cython. And Cython actually, this I had no idea about. I just wanted to talk to you about SageMath, but Cython actually came out of this project, right?
Yes, in the following sense. So when I started Sage, I mentioned before that Python plus the Python C API was kind of like the killer combination that meant that I could implement what I wanted in Sage on top of Python. So I had all these little benchmark programs, and I would try to implement them in other languages like OCaml, like these really fast functional compiled languages. And I would get something that was fast, but it wasn't quite as fast as I could write in C. And if you kind of look, basically, overall C lets you write really fast code, and Python lets you use C code to write new functions. But the Python C API is pretty challenging and potentially error-prone. You have to do manual reference counting all over the place, and the ways in which the Python C API functions work can take a while to learn. And I really envisioned a lot of people, including me when I'm tired or just really want to get work done, writing code. And I wanted to write a huge amount of code, and I didn't think it was really viable to write directly against the Python C API. I would mess up some reference counting and get seg faults, and that just wasn't what I wanted to do. And so I started planning to write some Python program that would generate code against the Python C API. And I got excited about the possibility of doing that. And then I started searching around and found a program called Pyrex, which is like the glassware, Pyrex, by Greg Ewing, who's a Python contributor. And he wrote this amazing program where you could write code. It looked almost like Python, but it would get converted into C extensions, and those would get linked into Python. And so that was really amazing, but it lacked a lot of functionality. Like it didn't have list comprehensions, and there were just a lot of little things. You couldn't do nested functions. Also, he didn't use revision control or anything, and he just kind of made it a zip archive every once in a while. It seemed like he worked on it mainly during the Christmas break each year or something.
Those were the early days, long ago, right?
So it was this was like 2004, 2005, and it was absolutely awesome project, but it kind of wasn't really going anywhere. And so I started adding functionality I needed to Pyrex, and that was, I mean, I don't really like writing compilers very much. It's not my thing. I'm not very good at it. But I had this PhD student, Robert Bradshaw, who I mentioned before, who now works at Google, and he started diving in and writing a lot of really tricky stuff and doing all these optimizations to Pyrex. And I thought that was pretty cool. And then another guy, Stefan Benel, who is the developer of LXML, which is a Python library, he was forking Pyrex to add all kinds of things as well. And then at the same time, I made up a project called SageX for making Sage faster. And it was just a combination of some of these Pyrex forks. The name was really bad, though, SageX, and we were just distributing it inside of Sage. So that was kind of stupid. And so after about a year of that, I looked at this book by Fogel called Producing OSS. It's on his website, producingoss.com. And I think it's inspired by the Subversion project. It's a great book. And I started, like when you read a book, to me, like when I read a book, I kind of as an exercise think about a lot of stuff while I'm reading the book. And so I started thinking about SageX and Pyrex. And then I was brainstorming for a name for this thing and kind of thinking, I should make this into a proper open source project. And then I came up with this name Cython, which is like Python, but C. But I thought it was a better name than SageX, which is hard to say and sort of doesn't have anything to do with Python or C. And so I Googled it, and there was only one hit which I could find, and it was a picture of this punk rocker in England who called himself Cython, flipping you off. And so I thought, I'm safe.
You'll probably not lay claim to this, really.
Exactly. So I thought I'm safe. I can choose this as a name. And then I talked to my PhD student, Robert, and to Stefan Benel, and I'm like, so I'm going to start this project and make you the lead developer. And each of them said no. And so I was a little worried about that. So I made them both lead developers and kind of like stepped back from it, made the website, bought the domain name. And though they both sort of decided not to be the lead developer, they together did an amazing amount of work and then other people started contributing. And I mean, it really has blown up huge amounts since then. So, yeah. And I did try to push their direction to make it so that Cython can compile all of Python. Like you could take the standard Python test suite and just build it and see how fast it is compared to Python. And the system's really got like deep because part of the test cases for Cython is compile all of Sage, which is huge, and then run the Sage test suite. And also there are sort of things we need, like when you're running blocking C code, you want to be able to hit Control C and have that interrupt the running code. And so in Sage, we put a lot of work into writing something that would let you interrupt blocking C code that was written using Cython. Martin Albrecht recently separated that out as a separate project that you can pip install, so you can use it in your own Cython code.
Right. Okay. That's really cool.
So that's kind of where Cython came from. And I think it's been steadily progressing over the years. Very often there are things that come along which kind of sound like they do something similar, but Cython's is just so battle tested. And no matter what, like if you want to write some fast code that you can use from Python and you're willing to understand the basics of C data types, you can use Cython and do it and get it done. And if you want to make some code that's usable from C or C++, like a C or C++ library, available to Python with no overhead, then you can do that via Cython. So it's very different than Swig, standard wrapper and interface generator, where Swig will automatically take a C++ library and make it usable from Python. But there's some Python code between the C++ library and and that slows things down a lot. So with Cython, we do things like make it so you can use a third-party library that provides basic arithmetic addition and multiplication, say in a finite field, and we can make that so it's very, very fast. So it just takes on the order of 100 nanoseconds to do additions and multiplications. So it really, really eliminates overhead and makes using very, very low-level C code possible.
Yeah, that's really awesome. How applicable is that in general? Is this something you would only use on math, or if you've got like a web service backend and there's a section that needs to go faster, would Cython be something you might consider?
I think it's really, really aimed towards very compute-heavy loads. So, like, it doesn't help much if your problem is I/O bound. And then, like, the new Python async stuff is probably way more useful, or something like Twisted.
Yeah, absolutely.
So it's really, really all about compute-heavy, non-asynchronous. You have a synchronous thing, like a for loop, where you have a doubly nested for loop that's doing some calculation in the inside. And you want to make that one part really, really fast, as fast as you could possibly write it in C. That's what Cython lets you do.
Okay, very cool.
And that's the sort of thing that comes up a lot in math programming.
Yeah, of course it does. Matrix multiplies and all sorts of things, right?
Yep.
So the sort of next step that you might take this whole project is, rather than having people download 800 megs of all those packages and run it locally, is just fire up a web browser. And so you started cloud.sagemath.com, right?
Yes. Yep. I started that in 2013. And my initial motivation was that I had been teaching courses for just repeatedly every year for about a decade to undergraduates on how to use open source math software for kind of math. So I get like 40 or 50 math or math, CS, stats, econ undergrads. And the whole course is about how to, program in Python, program in Cython, use lots of functionality from Sage, use NumPy, use LaTeX a little bit. And the installation challenges for the students were pretty bad. And so for quite a while, they would often just use the Sage notebook server we had running, but that could only handle maybe a dozen people at once. And it really wasn't very scalable. And all it did was give you Sage, so you could type in Sage code and see the output, but it didn't have a terminal and it didn't have LaTeX. And so I decided to write something that was much more all-inclusive, where you could teach a whole course about anything related to basically open source scientific software, and do it all in one unified place where the students in about 15 seconds are up and running. So that was the motivation, and something I've refined over the last few years. I've taught using it a couple of times now and written some research papers and a book all within SageMath Cloud. And there have been several hundred other people who have run courses using it now.
Yeah, that's really great. I can just imagine the first day of these sort of computational math classes where it's like, all right, so what we're going to do is we're all going to download this. Like, my download canceled. Mine won't install. Mine installed, but it won't launch. You're just like, why? This is not what this class is about, right? But you've got to plow through that if it's on the machines, right? So this is really cool. And, it's a really slick web app that you guys have built.
Thanks. Yeah, so I've been working on an enormous amount for the last couple of years with some input from Jonathan Lee and Nicholas Ruend, who are two UW undergraduates, and also Harold Schilly, who's been working on Sage since about 2007 and who lives in Vienna, Austria. So we've written this application, and it has, around about 4,000 users each day, and it'll often have about 400 active users at once. So it's pretty heavily used. And the usage is heavy because people are really running code, and they're running lots of Jupyter notebooks and Sage worksheets and editing LaTeX documents and maybe running long-term calculations. It all runs on top of Google Compute Engine, but it's also entirely top to bottom open source, and some people download it and install it on their own computers. Okay,
that's a really interesting component of it, that you can get the local server version.
Yep. And it provides, so what it gives you is real-time collaborative editing of terminals, Jupyter notebooks, LaTeX documents. It also has a course management system built in for assigning homework to students and collecting it. And everything's collaborative in that you can see other people editing, kind of like Google Docs. There's also chats and stuff.
Yeah, that's fantastic. And you've got a lot of features there. Like it's not just for, say, running Python code, but you can run C or Go, or there's the ability to open terminals, just a Linux bash shell or something like this, right?
Yep, absolutely. So it's kind of like those online IDEs, but like cloud9.io or one of those. But our target audience isn't at all programmers. It's just people who, especially students who just want to get up and running quickly with open source math related software. And we also have really good support for R and Julia and Octave and so on, especially because Jupyter notebooks have kernels for all these languages.
Right. You just pass it right along to Jupyter and let it deal with it, right?
Yep, exactly.
Nice. So you've got a lot of cool stuff in your GitHub, which I'll put in the SageMath GitHub, and I'll put a link to that in the show notes. And one of them I saw in there was stuff to do with Docker. How's Docker fit into this?
First, there is a SageMath Docker image that Eric Bray, who I think he's a guy in Europe, in France, who I think has the distinction of being the first full-time person to work on Sage. So NSF grants for Sage have kind of dried up recently, but in Europe, they just got this huge $8 million grant called Open Dream Kit. It's across the European Union, and it supports open source math software, including Sage. So the Europeans are really, really supporting open source math software. And Eric created some really nice Docker images for running Sage. So you just do like Docker run dash something SageMath /SageMath, and you're up and running with Sage. So it's yet another way of installing Sage. And there's a Jupyter version of it. So that's one thing. So SageMath Cloud doesn't currently exactly use Docker. We use C groups and a lot of the stuff that Docker's built on. But I think it will use Docker extensively in the next few months under the hood. You won't know the difference, but it'll just make things run a little smoother and be more scalable.
Yeah, and let the Docker folks manage that kind of stuff and not you, right?
Yep. Yeah, exactly.
Yeah, very cool. All right, we're getting kind of to the end of the show. One thing I wanted to recommend for people is, if this is all interesting to you guys, go to cloud.sagemath.com. You can create an account there and check it out. But there's also a video like right on the landing page there that gives the 2-minute story of this. It's if you want to share it, that's cool. And it features you and a bunch of other people in there, which is cool. And you've got some pretty sweet skating in there.
I own the biggest skateboard ramp in the Northwest, and I skate it a lot. So I'm really into skating large half pipes.
Wow, that's really cool. This is at your house?
It's at a friend of mine's house, thankfully. It's not at my house.
Nice. That's really cool. When I was growing up, my brother built a quarter pipe, so we periodically hurt ourselves on that thing. That was cool.
Yeah, I got into skateboarding with my brother. We skateboard together a lot still.
Oh, yeah, that's great. All right, so I think it's probably a good time to wrap up our conversation. So let me ask you 2 questions I always ask my guests. First, even though you can't pip install SageMath, there's still a lot of packages that you guys must use. And so do you have a favorite PyPI package that is really helpful to you that maybe other people don't know about?
Well, okay. Let's see. First, again, I really wish the answer was SageMath. I did. I posted my first ever package to PyPI. How do you say it? PyPI.
Guido says it PyPI, and some of the core developers say PyPI, and PyPI conflicts with PyPI, the runtime. So yeah, I'm with PyPI as well.
Okay, so I posted to PyPI a PyGSL package. So I'll say that that's a brand new one that wasn't there before. I did it because a physicist who wanted to use it in their class on SageMath Cloud wanted this. GSL is the GNU Scientific Library, and they wanted these Cython bindings to the GNU Scientific Library to be available. And the only way to do it was to download some zip file off of SourceForge. And that sucks. So
yeah, anything on SourceForge these days is a little suspect.
So I set up a PyPI account and figured out I took the zip file, then I pushed it. So I myself became the kind of manager of the PyGSL package on PyPI. And
yeah, lovely.
It took me about 2 to 3 minutes to learn how to do so. So my answer is that package, or push your own package, especially some old thing on SourceForge that should be pip installable, and make it pip installable. It's easy for anybody to make things pip installable.
Yeah, it's surprisingly easy to register a package and upload it and so on. You just more or less create an account and just use the built-in tools and the setup tools and stuff. Yeah, it's really nice.
Yeah, absolutely.
Awesome. And then What editor do you use when you write Python code?
So I dog food everything. So I do absolutely all of my development of SageMath Cloud and Sage from within SageMath Cloud. And the editor of SageMath Cloud it's built on top of CodeMirror, which is a a JavaScript-based code editor. So I added things like multiple panes, so you can split the view and see 2 points in the document at once. And also because the editing is synchronized, you can just open multiple browser tabs to see multiple points in the same document at once. And then I also have various plugins for the kind of functionality I felt like I really needed, like deleting trailing white space and so on. So my answer is CodeMirror, which is probably not the most popular answer, but it's my answer. Oh, one other thing.
I think that's really cool.
One other thing is in SageMath Cloud, there's a history. So whenever you edit, every keystroke almost is recorded. And there's a slider that lets you slide back and forth and see all past versions of your document. And so like when I'm editing code, I'll be like, oh, I want to look at what it was like 3 minutes ago or 10 minutes ago and copy something from that. And you can very easily do that with a little slider. So you get kind of a whole third dimension of time when editing. So it does have some benefits.
Yeah, that's a really nice feature. I feel like a system has reached some level of maturity and well-roundedness and goodness, basically, when it can create itself. When you compile C with a C compiler, when you write like PyPy, you run Python with Python, these types of things. It's pretty cool. So it's nice to hear you're doing that for your editor. Awesome. So before we say goodbye, what should people know about getting started with this? If they want to check it out, what should they do?
So just type Sage or SageMath into Google and you'll get to the sagemath.org website. And that has all kinds of documentation. There's like probably 10 to 15,000 pages of documentation there, links to books and so on. And there's a big link to, which just says SageMath Online. And if you click that, it takes you to the SageMath Cloud site that we've been talking about. And there's also something called SageMath Cell, which gives you one single input box where you can type in a block of Sage code and see output. And you can also embed those blocks inside of your own static website easily. And there's an API for doing that. So go to the website sagemath.org. You can either download it or go to the cloud site and use it online. It's all 100% open source, top to bottom.
William, this is quite an achievement. I really love looking inside of it because you solved a lot of cool problems and a lot of excellent technologies come out of it. So congratulations.
Thank you.
Yeah, it's been good to talk to you. Take care.
Okay, thanks a lot. Great talking to you.
Yeah, bye. This has been another episode of Talk Python to Me. Today's guest was William Stein, and this episode has been sponsored by Hired and SnapCI. Thank you guys for supporting the show. Hired wants to help you find your next big thing. Visit hired.com/talkpython to get 5 or more offers with salary and equity presented right up front and a special listener signing bonus of $2,000. SnapCI is modern, continuous integration and delivery. Build, test, and deploy your code directly from GitHub, all in your browser with debugging, Docker, and Parallelism included. Try them for free at snap.ci/talkpython. Are you or a colleague trying to learn Python? Have you tried books and videos that left you bored by just covering topics point by point? Well, check out my online course, Python Jumpstart by Building 10 Apps at talkpython.fm/course to experience a more engaging way to learn Python. You can find the links from this show at talkpython.fm/episodes/show/59. Be sure to subscribe to the show. Open your favorite podcatcher and search for Python. We should be right at the top. You can also find the iTunes feed at /iTunes, Google Play feed at /play, and direct RSS feed at /RSS on talkpython.fm. Our theme music is Developers, Developers, Developers by Corey Smith, who goes by Smix. You can hear the entire song at talkpython.fm/music. This is your host, Michael Kennedy. Thanks so much for listening. I really appreciate it. Smix, let's get out of here.
Stating with my voice, there's no norm that I can feel within. Haven't been sleeping, I've been using lots of rest. I'll pass the mic back to who rocked it best.